So I think that if something marked this past year, I would say in transformers has been vision transformers, right? I think that they have driven a lot of the hype that has been around. If you go on Twitter, you see a lot of vision transformers popping up ever since this an image is worth 16 by 16 words, I think. That is already super famous, has a lot of citations. So Mostafa was part of that project. I'm really happy that he could also make it this time as well. He's also repeating from the first workshop. So yeah, so please.
Cool. Thanks for having me, and thanks for basically all of you to coming. This is actually pretty amazing. I kind of like forgot how much we are missing with the in-person events, and this is really great to again see friends and I don't know, like fist bump with some of you or something like that. This is amazing. All right, cool. I wanted to actually basically talk about, so when Jakub reached out and said like we're going to have the second edition of the event, I was like, okay, we have a bunch of cool like fresh out of the oven work for sequence modeling with transformers, like OmniNet. We have a bunch of things that they are actually doing an amazing job in many different tasks, and I wanted to talk about that. But on the other hand, I wanted to also, given the fact that I've been also working on vision and multimodal setup, I wanted to also maybe just talk about vision transformer and how transformers are working on vision application and tasks. So basically, I ended up talking about vision transformer and preparing a slide for that. And might be interesting for some of you, might be a bit like off topic, but I'm pretty sure in a few years, they're going to be like all multimodal transformers. And probably in, I don't know, in a few editions of the transformers at work, we are going to have more than half of the talks about like how to read a homepage for retrieval and encode images, if there's audio, video, everything, text, and then retrieve that. And for that, I think transformers are amazing to be a good backbone for such a multimodal, given that they just deal with tokens, no matter what is the token. Is it a subword? It's a patch of an image. It's a cube of a video. It's part of a spectrogram and everything. So this is really great to have this opportunity to basically talk about like at least one of these modalities besides text. And I just want to start with the fact that similar to NLP, that we had like LSTM and RNNs everywhere in 2017 or even before that. We had CNNs and CNN convolution-based models also everywhere in computer vision. And then when I started at Google, co-locating with the vision team, I was working on transformers, and like we had a bunch of people working on transformer for vision, but it never worked out. And it was a bit of like mystery, because why it doesn't work on vision. You know, we had like different things. I remember even at like I had one singular slide last time in the previous edition about I talked about axial transformer, which was like a preview for transformer on vision. But it never got like the SOTA, or it never got actually over like the performance of convolutional models. And the whole thing actually started when we started actually looking into large scale data set and scaling up and using these transformer models in the transfer setup, where you have like pre-training phase, and then you just transfer the knowledge via fine tuning or like few shot or anything. And then we had the luxury of having a large scale labeled data, like a lot of heroin, as Rodrigo said, you know, like a super addicted. So we had this JFT data set, which has 300 million images labeled. It's all kind of like weakly labeled or federated labeling stuff happen. And we actually have a 2 billion version of that data. So I'm going to talk about that in short. When I look at Thomas, I feel a bit like shamed that we don't have this data available for everyone, but hopefully at some point it's going to happen. Who knows? Yeah, but I'm not part of that decision like that. But when they made this decision that, oh, we're not going to make this public, I wasn't there. So yeah, anyhow. All right, and transformers, I'm going to skip this slide, but it's just basically self-attentions and feed-forward network exploits, and then we just stack a layer of them, right? And then what is great about them is that, first of all, you have, compared to like convolutions or LSTMs, you have this global receptive field that you can basically contextualize the representation of every token with respect to all the other tokens that you have. Is it a good things or it's a bad things? It's like a powerful feature. We're going to get back to this. You have this, again, parallelization ability. CNNs also have that, but like RNN or recurrent neural network, they don't have it. They're surprisingly not super efficient. Again, we're going to talk about this. I mean, if you have an LSTM or RNN-based decoder, sometimes it's much faster than transformer decoder. So if you don't use the parallelizability, which you do during training. So during training, you have either encoder only, or even if you have this like encoder decoder, you do teacher forcing. So you do like parallel training. So you never do autoregressive decoding. So but during inference time, it might get super slow. And another thing that actually is a bit like vision related is that it gives you the chance for learning object-centric representation. So convolutions, they actually process the image as a grid of pixels, right? So you basically like slide a window over the image to learn representation of different parts and combine these, and then at the end of the day, you just output a representation. But the point is that for the sky up there, you don't want to spend, I don't know, if we get like each square as a unit of compute, you don't want to spend like, I don't know, 6 units of compute for a sky where there's nothing happening there, right? But if you manage to find a way to just represent the whole part as a token, and then spend like, I don't know, the amount of compute that you spend on that part is equal to this backpack or the hand of this person, it could be more efficient. So you don't want to distribute your compute like uniformly across the input. And transformers actually give you this chance. Vision transformer doesn't do this though. Again, but this was one of the things that we actually did. The project was called Off the Grid. We've been playing with that for a long time. There's also one paper out from Google, which is called Slot Attention, and there's also Deter from Facebook that has the same motivation for learning object-centric representation and basically having these latent tokens that are representing objects as opposed to, I don't know, like a group of pixels. So vision transformer is extremely simple. We actually did a lot of more complicated things, but we ended up just going back and then take the simplest one and stick with the transformer architecture that people just use in a sequence modeling language without doing any change or without applying any like a fancy feature to make it translation on invariance or something like. But it's just basically we just take the input image, divide it into non-overlapping patches, and then just represent that as a sequence of patches, embed them using a linear projection. This is a convolution operation in case someone says that there's no convolution in vision transformer. There is a convolution, but I don't know if you want it. I mean, everything is convolution. But yeah, I mean, anyhow, yeah, I don't know. I mean, if it's really easy to get Schmidt-Hubert. So I say that it's not like cannot say that it's convolution free, but like the way that you can implement it without convolution. But basically, it's like a convolution with the patch size and the stride size of I don't know, 16 by 16, and then you attach this positional embedding to the sequence, which is supposed to capture the position of these patches. It's 1D positional embedding, although we had these tokens coming from a 2D space. And then you have a transformer encoder, just whatever you use for language. And then you have an NLP head, and then just take the CLS token representation of the encoder and then map it to the class space. We had this is actually from the original paper. It's a bit out of date. But we had a different sizes of the model. And when we talk about a width, like large, like L means large or base or huge, and /16, we mean that this is the size of the model and this is the size of the patch. So you can have like the same number of parameters, but operating on bigger patches or smaller patches. And then we realized that basically for the data set that we are working on, 16 by 16 is pretty good. It's not too big to not capture the details that we want, and it's not too small to give us unnecessary long sequence to deal with when we are encoding. And this is not like basically this quadratic complexity of the self-attention kicks in if you want to go to 8 by 8 or 4 by 4. And then the hybrid one is simply, okay, let's get rid of this convolution, this simple convolution for patching and like tokenizing, and just use as like a ResNet, a mini ResNet or a ResNet 50 or even larger ResNet, and then on top of that, we just get the representation out of the ResNet and then linearize that in a sequence and then feed it to a transformer. And then we, as I said, you don't see the benefit of width when you're working on smaller data set. And then when you move to larger data set, you can see that it actually start working really greatly. And what is great about it is that it gives you a really nice performance compute trade-off compared to convolutional models. So this is a efficient net and bit large, which is a ResNet 152, which is from this big transfer paper. These are the results that are actually, they've been somehow state of the art for many of these data sets, especially on the few shot training. And then we had this width huge, which was 5 times, is it 4? 4 times, it takes 4 times less compute, and it actually gives you much better results. So in terms of this trade-off that we were looking for, it was doing a better job in that large scale and large data region. And then we had also like with large, which was not as good as with huge, but it's still pretty reasonable in terms of the performance that we are getting out of these models. And then we also had it trained on ImageNet 21K. Later, we have another paper from our group that they showed that with a little bit of regularization and a little bit of like, I don't know, like random argument plus mix-up plus like stochastic depth, you can basically get the scores that you get from JFD when you are just training your model on ImageNet 21K. All right, and then when we look at the learned positional embedding, we notice that actually the model just captures the this 2D shape of the input, while we did not represent anything, or but we noticed that some of the things were not like really necessary. As I said, they padded to, I don't know, like 256 tokens. So we're just removing that and then doing a global average pooling was a better option. We had like this, like we were memory banned when we were scaling up. Another one was basically just like optimizer we started actually. So we've been using Atom, but Atom keeps the 3 times compute, 3 times size of the parameters for doing the backpropagation. But we moved to the auto factor with some modifications, and then basically a little bit of a small things to how to scale up transformers to larger sizes. Another thing that I wanted to talk about is this video vision transformer is somehow the continuation of the vision transformer on videos. So we wanted to know how to do video action and entity recognition, just let's call it video classification. And then what we wanted to do was basically, we don't have such a large, at least available, like large video data set externally available. And then we wanted to know that if you have a VIT model pre-trained on ImageNet 21K, can you, like on images, can you somehow some sort of like use some like surgery of the weight to use that in the like a video setup? And then you have basically a sequence of images, and we had this model which we call it Vivid, and for the input encoding for the patch extraction, we had two simple ideas. The first one was, okay, just let's try patches from each frame separately and then concatenate that. It's going to be a long sequence, expensive. Another one is basically, let's go for 3D patches, which is somehow a 3D version of the 2D tokenization in the vision transformer. And then we had a bunch of tricks to basically reduce the cost, because the sequence length is pretty large and long, right? So and the first one was, okay, let's actually do some sort of factorization, or basically like applying the model on different axes. And then we had like factorized encoder, which is running an encoder on spatial tokens and then on temporal tokens. We had another version which we had like different part of the model attending to different axes. And the last one was basically we somehow manipulated the heads to half of them attending to spatial tokens and the other half just attending to the temporal tokens. We got really good results. I don't have time to go over that, but we got basically SOTA on Kinetics 400, which is the ImageNet of videos, or super glue of videos. And oh man, please. Okay, how? Oh, good. Okay, I got stressed. And then we also noticed that some of these tricks, like factorizing the encoder, actually gives us a really good boost in the efficiency while not losing on the performance side. And as I said, you might end up actually using these models in like when dealing with long sequences, for example, like megapixel images or videos that we just talked about. And then this is going to be extremely expensive. For example, the COCO data set, like the resolution that people work with is like 130,300. And with a patch size of 16 by 16, you get to 7K sequence lengths, which is extremely large and expensive. And then we started actually trying different variants of transformers that are efficient in terms of dealing with this quadratic complexity or long sequences. I don't want to go through the different categories, but there's actually a really nice server if you're working on transformers on long sequences, documents, just try those. These are actually some, and I have some opinion. If you want to do that, just talk to me, because I tried like almost all of them. And if there's no author from these papers, I can just freely share my opinion about like which one you should take. Does that mean that we are saying goodbye to convolutions? Maybe not. It reminds me of, we don't have LSTM at Work workshop. Do we have? No. Maybe we just say goodbye to convolutions. Maybe not. What we know is that convolutions still, they have this like good inductive bias, which is needed for like images or video processing. And this is extremely important for low data regime. So if you don't have data, that inductive bias is going to give you a good boost in the performance. It's going to help you, while the vision transformer doesn't have that. And you might think about other options, like distilling the effect of inductive bias, like what Date does, or just use a hybrid model, which has also some convolution. And the point is that if convolutions are going to stay around or not is also a little bit about this kind of lotteries that we have in machine learning, right? So like the hardware lottery you don't get like to work on sparse computation simply because we don't have a hardware that like amazingly support that. Or the benchmark lottery, as long as, I don't know, you have super glue, maybe convolutional models for sequence processing never going to take off, because simply what they need is this like soft matching or cross matching across these two sentences, and convolution, they don't have it. So they win the benchmark lottery, while if you had different benchmarks, maybe convolutions were the de facto choice for sequence modeling. All right, I just also want to simply say that we just open sourced a library which is called Scenic, and like many of these models and projects were done in this project and in this code base or library, and we're going to, I mean, it's just open source. We are going to release a lot of different things, so take a look and let me know. And thanks for today. And these are all the amazing collaborators.
All right, thank you very much. it's really interesting. So I already see some hands.
Nice, thank you.
Sure.
So I'm wondering how the results would be affected if we change the order of the tiles, the way that we present it to the model, because like in language we have that like sequence has meaning. If you move the words in a sentence, then the meaning changes. But in vision, you can change some tiles and like you still have a building there in the in the picture.
It's actually a great question, and we have a project that just ended like last week. It was an intern project. We're going to have a submission to iClear probably next week, and it was about like how robust is vision transformer with respect to the cases that you need to get the global structure, right? So what you're saying is basically is needed. So if you really depends on local texture, it doesn't matter like where in which order you take these tiles, right? But if there is something big and this global structure and the order of these matters, vision transformers are not best in terms of being robust against that. This is true. And that paper actually, again, I don't know how much I can share, but it does something similar to language for discrete tokenization to make it better for vision transformer to make use of this positional information. But what we understood that if we just reshuffle these in like an ImageNet, you don't lose that much compute, which means that the model really doesn't pick the pattern that is depending on the global structure. It's actually just basically based on local features decides what is in the image. But that's actually a really nice thing to look into basically the robustness of the model in different scenarios.
Thank you. So a lot of the good things that BERT brought to NLP was that it was mask language model. So you don't need labels basically, right? But for VAT, so far you do need labels and a lot of labels.
Yeah.
And there is work on not having them, but I would like to know your opinion on that and what you've seen that's worth noting.
Absolutely, there's no way to survive depending on supervised learning. Like it's heroin, you know. I mean, it's like end of the line. But yes, that is true. We've been also working on self-supervised setup for training bits. There are already some research. I think BAIT is a recent one which does BERT style like vision transformer. And again, part of the work that I just mentioned is also about how to do this self-supervised things by mapping this token to discrete elements that you can do some sort of masking. So instead of like having patches presented as embedding, if you have them as integer tokens, you might be able to do that. How do you do that? Like there are also a lot of research about like the quantization of the continuous space and stuff like that. But yes, and there are research going on for like, and we are there, and hopefully soon we will see what are the tricks and what are the ways that we can actually just do self-supervised training for having vision transformers.
I think there was something. Yeah.
Okay, thank you for the interesting talk. You mentioned the multimodal transformers that are going to come in the future. How do you imagine that? Is it kind of similar to positional embeddings, but instead of position, you encode the media type, or is it something different?
You can do all sort of things to basically encode the information of the modality, but sometimes you don't need it. I mean, again, it really depends on what data regime you're working on. If you're working on large data regime, I mean, I just trained like a model that works on video, audio, images, not text, though it was difficult to actually get it working also with text. Co-training these, and then I had no token to tell the model that this set of tokens that you're processing is coming from an audio or from an image, and it's working like a charm. So again, it's pretty much the magic of like large scale training. But of course, this is something that you can always make it explicit in a model and add a signal that tells the model what modality you're encoding.
Yeah, that's impressive. Thank you.
Sure.
Thanks for the talk.
Sure.
Are there any known adversarial attacks to these visual transformers just by changing the order of the tokens just a little bit? Like that might look like the same picture to us humans, but the neural network will decide completely differently.
I unfortunately am not expert in that, and I've never worked on actively on a project that actually kind of evaluates these models in terms of how they're robust against adversarial attacks or something like that. And but there's one paper already out, and there's actually a really nice library. I think it's like robustness metrics or something like that. And then they have a paper that they compare convolutions versus like convolutional vision models versus like transformer-based vision models. And I don't know if they actually had the specific case that you just mentioned. Generally, I don't know the answer to your question. Could have said that sooner, but it's under research. I'm pretty sure that like many people are looking into it.
All right, let's go to the back.
The human eye is really good at getting the picture even at low resolutions.
Yeah.
Can you work with codecs to reduce the resolution or some lossy compression?
That's actually one of the bigger things that we're looking into in the video modeling, simply because the amount of information across frames doesn't change that much. So we wanted to know that how much we can compress each frame without losing, because like, you can imagine that, okay, I have this consecutive set of frames, and then if I do some sort of compression on that, which I go to lower resolution, maybe I can recover what I can, like what I need. And it's like a little bit of extra information that I never use in the video setup. So far, we couldn't manage to do that basically in a way that we always lose some. It's also like a localization task. It's actually like tracking on object detection across frames. So it's actually extremely difficult. But what you're saying is it is possible, and it really depends what is the granularity of the label that you are asking the model, right? If you're asking if there's a dog or there's a cat in this image, maybe it's possible. But if you want to say that, just give me the pixels that shows number 6 in the cell phone on the hand of this person, maybe not. But there's no like a single answer for that. It really depends on the application. But that's actually a great idea to reduce the cost of vision transformers, to go to lower resolution when it's not needed to process high resolution images.
All right, so we're gonna do 2 last short questions.
Hi, Mostafa. Thanks, great talk. I wanted to pick up on something you said about convolutions, like you were saying, we don't have, maybe we don't have any convolutions anymore in a while. But I was reading a paper recently about convolutional language modeling and comparing it to transformers, and you were actually on
exactly
on the paper.
On that paper, yes.
And I thought the claim there was, convolutional language models might actually be on par with the transformers. And I thought maybe we are seeing, the return of the convolutions here, because a lot of, if you think about language, a lot of the newer transformers, when they do language modeling, so not vision but language modeling, they're doing this, local attention, which is not, when you come to think of it, entirely unlike a convolution now, is it? I mean, so since you were on the paper, I just wanted to ask your.
This is actually a great point. Yes, that paper led to another paper that we wrote, which was a position paper, the benchmark lottery. I don't know if you've seen that or not. But we discussed the fact that how come some models or class of models, they just disappear? What happens? Is it because they're like, or why we choose one model and work on them? Is it because they're like inherently better, or is it like because of the true merit of the model, or it's just something that is like the artifact of I don't know, like this research community that, I don't know. For example, I want to say that there is, I don't want to say that the possibility of convolution picking up and then coming back and then just like remove all transformer, it's not zero. But on the other hand, it's a bit unlikely, at least in short term, simply because as a researcher, the easier things is to do incremental research. And if I want to do incremental research, it's easier if I just pick the best model on the leaderboard, right? I don't want to say that that's true.
But they're just bound to be much faster. They should.
The convolutions, you mean?
Yeah.
Absolutely. Yes.
So that's why the word is my.
That's actually also RNNs during decoding. So that's, I think this is one of the probably points that when people start pushing these models into production, they're going to start realizing that, oh, you know, like it was super cool to do research, but like when we go to the inference time, we just see the cost, right?
Yeah, so that's what I'm saying.
Yeah. Sometimes you just spend like a lot of money on the research on these models, and you say, okay, you know, whatever, I'm going to spend a bit more and increase the number of chips and then push this model to production. Sometimes you are wise and you don't do that. You go do a convolutional model, train a convolutional model and put it. But I totally, I was actually having a conversation with a colleague yesterday, and this is a big challenge in production. Like these transformer models, especially like during decoding, they're extremely slow compared to the alternatives. Sometimes and we never spend good amount of time to scale up LSTMs. You know, maybe if we do that, if we spend enough time and energy on those, maybe they work much better, right? But yes, I think that's actually a great chance for these expensive models to again find themselves a bit hard to be on top again for every application and production.